Okay, sweet. So, how many sigma and pi bonds are present? This is another practice. We're going to go over it really fast because practice makes perfect, and it'll help out a lot in the end. Hopefully, the other review videos for this have practice as well because it helps a lot. So, there's a nice little carbon chain that has some double bonds, some triple bonds, has a nitrogen and oxygen and some carbons. So, carbon chain. Remember all the rules with that. I'll count them out. To start, I'll give you about 10 to 15 seconds. If you need more time, you'll just be able to pause it afterwards because it's just a video. Just wait 10 seconds. Alright, sweet. So, the answers are 17 sigma and 4 pi. Don't forget the hydrogens. It is a carbon chain. So we're going to use white to mark it out. So we're going to go through and just mark up all the hydrogens because it makes it easiest. So right here's a carbon. 1, 2, 3. Perfect. That one, the carbon's happy. 1, because there's 1, 2, 3 bonds already present. Needs one more. This carbon is 1, 2, 3. Needs one more. Happy has 4 bonds. Oxygen doesn't need anything. This carbon only has 2 bonds, needs 2 more. 1, 2. This one as well. 1, 2. So there's actually a carbon right here as well. That's because triple bonds can't bend, but it's happy anyway. And then nitrogen, you're good as well. So we're going to go through and mark up the sigma bonds and the pi bonds. So first we'll do sigma, because that'll be easiest. We'll use purple, because we're feeling good today. So there's purple, and we're going to go 1, 2, 3, 4, 5. We know there's one in here. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, one more, 17. Okay, so we have 17 sigma. We'll count the rest as pi. We'll use green. 1, 2, 3, and 4. So there's 4 pi bonds. Do not forget the hydrogens. When there's carbon chains, they'll trip you up, and that won't be so good. Okay, so there's a rule breaker. This is the reason why the valence bond theory kind of started going south, is when they realized that beryllium, for example, can bond with 2 hydrogen, but beryllium has a full s2 orbital, which technically breaks the rules. So they had to adapt the valence bond theory to fit it. So they came up with the idea of hybridization to prove that it's possible that beryllium can work like this. So we're going to go over what that is. Okay, so hybridization, I forgot to draw that in. So basically, we're just going to mix the available orbitals and keep the number of total orbitals the same. So we're going to just gotta draw this in really fast. I totally forgot to do that. Okay, so there's beryllium right there. I hope it's beryllium. The Be. To P. So this is what we're working with. Be. H2. Okay. So originally beryllium is like this, and we know that it can't bond like this because the orbital's filled and there's nothing here to go to. So we're going to keep the total number of orbitals the same. So notice there's 1, 2, 3, 4 orbitals present. So we cannot break that. 1, 2, 3, 4. So what we're going to do is we're going to hybridize an orbital to fit our needs. So we can see here that we need 2, 1, 2 to make the hydrogens happy. So we're going to go take a p and convert them into sp orbitals. So we have 1, 2 orbitals, but in total we still have 1, 2, 3, 4, just like up here, 1, 2, 3, 4, which is money. Okay, so these are the basic rules of hybridization that he gave us that kind of make things easy. So just mix to get the number. Whoops, that's a misspell. Pretend it's a B. Just mix to get the number of orbitals you need. Don't try and overcomplicate it. Don't overthink it. Just go to what you need. Remember that both lone pairs and single bonds need hybrid orbitals. To figure this out, draw a Lewis structure to see where everything is and what you will need. You're going to need to find the steric number, which you know is like the bonding places in the lone pairs, how many there are, and make enough hybridized orbitals to match the steric number, which is what we just talked about. Okay, sweet. So for example, really fast, let's draw this out. So do it like H2O, H. Okay, so really fast, count out the steric number for this. So we have one lone pair, two lone pair, one, two lone pair, then one, two. So there's four things here, which means the steric number would be 4. Woo! Sweet. So, next slide. Okay, so these are the hybridized orbitals that we're going to have to cover. And this is basically all of them. We're not going to go past this down here, and we're not going to go below that. There's actually nothing below that. But that's what we're going to work with. So, just to draw it out so it makes sense. I saw this the other day and it totally made sense to me. So S plus 1p. And that's going to make one sp orbital. But we know there's 3 p orbitals, so we're going to have sp. And there's going to be 2 p orbitals that are left over. And you're going to see that on the next slide what it looks like. Right here, same thing. There's S plus 2 of the 3 present p orbitals. So there's going to be S2p, and then there's going to be 1p left over, and you're going to see on the next slide once again. Same idea, sp3, but this time it's going to use all 3 p orbitals. So that means this next one right here, sp3, it needs one more orbital. There's no more p orbitals. It's going to drop and take one of the d orbitals. Same thing right here, sp3, take another two of the d orbitals. And these are all of them, so just count it. So there's 1, 2 letters, 1, 2, 3 letters, 1, 2, 3, 4 letters, 1, 2, 3, 4, 5 letters, 1, 2, 3, 4, 6 letters. Okay, sweet. So, like I said, for the sp orbital, remember it's one s orbital plus a p orbital. So there's 3 p orbitals present. So that means there's 2 p orbitals left over. So right here we can see, look, there's there's the sp orbitals, and then right here there's 1 and 2 p orbitals. Same thing here. We know that there's 1 p orbital left because 2 are being used. So we can see right here, the blue is the p orbital, by the way. And then same thing, sp3, all of them being used. sp3d, we're expanding to the d. sp3d2, same thing. Okay, so these are the number of sigma bonds that could possibly be present in each one of these things. And then these are the molecular geometries. These are going to be important. So you can also just think about it like, for example, the T shape. There's only going to be 3 bonds because there's going to be 2 lone pairs sitting up top. Same thing with a linear. There's only going to be 2 sigma bonds because there's only 2 single bonds and 3 lone pairs. If that makes sense. Like a, I don't know, like a H xenon to an H. Xenon expands octet. It's going to go 1, 2, 1, 2, 1, 2. So look, there's only 2 sigma bonds right there. So that's kind of it. Then there's the angles. Those are really important. So these are on the slides. This thing, I took it from his slides, so you can just use it to get to it and study it. Perfect. In addition to going over how many sigma bonds are in each thing, we can go over how many things are how much they repel, which goes right with the angles of the orbitals. So angles between the hybrid orbitals. So just focus on this to that one like that. So, like we talked about in the beginning, the orbitals are just going to push each other around, which is how the valence bond theory can help us determine the shape of this molecule. So, like we can see right here, this one's going to be 180 degrees, which means we think it's going to be linear, because this is where the electrons are. This is empty. These p orbitals are empty right now. Same thing here. So right now we know this one right here. For example, where's the laser pointer? sp3. All the p orbitals are filled, and the s orbital. So everything's just coming together to bond. So now we know that it could be a tetrahedral, it could be trigonal pyramidal with one lone pair, or bent with two lone pairs, like the water we just showed, the H2O. So basically, this kind of proves how they kind of help you come up with the geometry, molecular geometry. So once again, we kind of look at it. We'll go off just because we've already used it right here. Let's just do that water again really fast so we can see it all. Okay, so we know there's 1, 2 lone pairs, 2 bonds. So we know it's going to be this one right here. So we can look how many sigma bonds. There's 2 sigma bonds because there's 2 single bonds right here. 1, 2. So we can look down. There's not 4, there's not 3. There's 2. Bing. So that means it's going to be bent. Okay. So the angles is just for this one basically. It's going to be the same. There's going to be 109.5 between these. And same thing here. It's going to just kind of repel it all equally. Alright, so now we have some practices. Okay, so two last really quick questions to just kind of help us solidify this. So what's this hybridization of this molecule? Take your time, pause the video if you want. I'll count to 10 in my head and we'll call it good. Okay, sweet. So let's count it out really fast. We use white. So we're going to find the steric number. 1, 2, 3, 4, 5. So now we got to figure out which one of these right here is going to go with the steric number of 5. Okay, so sp3, there's 1, 2, 3, 4 orbitals being used. Does that match the steric number of 5? It doesn't. sp6 does not exist whatsoever. That's a lie. I'm a liar. sp2, there's only 3 orbitals being used. sp3d, 2, there is 6 orbitals being used. That's 1 too much. sp3d, 1, 2, 3, 4, 5. Money. So we're going to go with that. This is the right answer. What we just went over. E is the right answer. sp3d. Okay, now we're going to the molecular geometry. So think about it. What's the molecular geometry of this right here? And I guess this too. This is the same thing. Just different example. Maybe different atoms. So, same thing. Count it out in your head. Give it about 5 seconds. Pause the video. We're going to go over the answer. Okay, so once again, we're going to look for the steric number. We know the steric number is 5 because it's the same molecule, but we'll just count it out anyway, just in case. We have 1, 2 lone pairs, 1, 2 lone pairs, 1, 2, 3. So the steric number is 5. So think about it for a second. How do we know which one that's going to match up with? It's going to be T-shaped. Perfect. You guys can look that up too. Okay, sweet. So once again, there's all those other helps at the beginning of the presentation, and they're super, super helpful. They have a bunch of examples that go with them. Practice makes perfect. So reach out to Dr. Mortensen or your TA. And yeah, smash the final, baby. Yeah!